Our next paper in the second session of ICFP 2020 is going to be stage selective parser combinators, and it's going to be presented by Jamie Willis and Nick Wu.
Hello, can you hear me?
Hello, yeah, I can hear you.
Nice, I can hear you too.
So I don't know if we've met. My name is Nick Wu. I'm from Imperial College London.
Oh, hey, I'm Jamie Willis. I'm also from Imperial.
Ah, what a coincidence. It's strange doing an online conference with pre-recorded videos, isn't it?
Yeah, ICFP's format is interesting this year. I wonder if anyone's made the most of it with their presentations somehow.
Indeed. So what are you working on?
I've been working with parsers.
Ah, nice. I'm a big fan of parser combinators.
What are those?
Oh, well, they're a way of building a parser that follows the structure of a grammar closely by treating parsers as first-class values and building larger parsers from smaller ones.
Right, can I have an example?
Let's look at the BNF for a language that recognizes strings of characters. Let's suppose that they're non-empty. So here's some code. The non-terminal alpha is the choice of letters from A to Z, and alphas consists of one of those, followed either by more alphas or by epsilon, the empty token.
Okay, so how do you actually write the parsers then?
Right, and so in Haskell, alpha is a value of type parser char, since it parses a character, and here we simply give the alternative between each of the chars. The alphas parser returns a list of chars by first parsing an alpha, and then appending it to the result of more alphas or just the empty list.
Right, so how does that strange cons thing work?
Okay, so parsers are applicative, so we can lift normal functions and constructors like cons so that they can work on parsers. So here the pure cons just makes a function work at the parser level, and then the app, which is the star, will ensure that px is parsed first, followed by px's, and then it's put together with cons.
That doesn't seem like something you could execute.
Well, if you want to actually run one of these parsers on an input string x's, then you use the run parser function that will take the string and return the parsed result if it can.
Right, so those combinators seem really verbose. I usually just use eBNF like this, where you'd use a character class and a plus, and it gets rid of a lot of the bloat.
Oh, yeah, sure, that makes sense. Well, you can also do this with combinators as well. Here's what you do with alphas. We're using one of, which will take one of the A to Z in the range as you've done, and the plus says that you simply want some of those.
Ah, that's neat. Okay, so how are one of and some implemented?
Well, they're also in terms of simpler combinators. One of is in terms of the primitive satisfy, and satisfy takes a predicate and accepts an input character that satisfies it. For one of, we simply want it to be an element of a given list C's. Some can actually be implemented in terms of what we've seen so far. Can you see how?
Sure, let me see. I think if I took the alphas example, I could reverse engineer it. So I guess if I factor this alpha out, then that would give me some. So I'd replace alpha with some px and then alphas with some px.
Yeah, that's right. And you could furthermore factor out what's inside the brackets to have both an implementation of some and many.
Right, so if some is the eBNF plus, then many's the star? But using parser combinators surely has a performance impact.
Right, yes. So there's definitely some overhead to using these kinds of combinators. But on the other hand, if you represent these combinators as a deep embedding, where the combinators are all data constructors, then you can do things like grammar analysis, which is driven by various laws, such as the applicative and alternative laws.
I guess you could optimize it that way. I think it's easier to understand performance by thinking of an underlying stack machine.
What do you mean?
Well, you can represent parsers as a machine with one stack for intermediate results and another for handling failure. And then you pass by executing instructions that interact with these stacks when they're given some input stream. So I guess we'll take your previous parser as an example. So here it would be.
Whoa, is that really still Haskell?
Yeah, sure. This is clearly just a recursive machine reading alphabetical characters, setting up failure handlers before recursing again and combining elements of the stack. What's there not to understand? Isn't this how you were taught to use Haskell?
Well, I think you'll have to go a bit slower than that for me.
Right, sure. So just read those dollars as semicolons in your favorite imperative language. Then alpha is similar to yours. It's just an instruction that verifies a predicate on the next input token and then continues with another instruction K. And alphas performs alpha and then leaves its result in the stack. It enters a catch block to handle any failure. And inside this block, alphas is ran again, which leaves its result in the stack too. and the two results are combined with lift2 cons. Then things are free to carry on with the next instruction K. But if failure happens, then the first few instructions of that second block before the case check that the input hasn't changed since starting the catch. And the case instruction then uses that information to either fail or combine alpha with the empty list before continuing with that same K.
Oh, I see. So your representation is much more explicit about control flow than mine.
Yeah, analyzing the control flow in my machine is quite straightforward. I think this is a lot more complex in your case.
Yeah, that's true. The control flow for the grammar isn't obvious at all until you start looking at something like derivatives.
Okay, hang on. I think I can see what's happening here. The representation that I have is the same as yours. It's just been transformed into CPS, continuation passing style. That's what makes the control flow explicit. Basically, each instruction takes as an argument the next instruction executes, and this is interpreted by passing around two continuations at runtime, the good continuation and the bad one.
Of course. So if you can convert between the two representations, then you'll be able to get both the high-level optimizations and grammar analysis of my approach, and the low-level optimizations and control flow analysis of yours. You get the both of both worlds. There's a problem, though. The machine you showed me before is untyped. How can we convince ourselves that the translation is working properly? My combinated tree is fully typed.
Well, my stack represents what's already been computed, right? I guess in your world that corresponds to combinators that have already been executed, and each combinator will push exactly one thing to the stack if it's successful.
So what if we can propagate my type information into a type level stack? Here, let me show you what I mean. So Halt is basically produces a machine that expects an A on an empty stack and returns that A.
Wait. How does that get implemented?
I see. You just use an H list. It's a heterogeneous list so that the values can have different types. The types of each element are kept in a type level list, and this list is the same as the one that will appear in our instruction types.
Oh, right. Okay, thanks for that. Carry on.
Right. Where was I? Okay, so push takes an X and a machine that expects X and X's and produces a machine that expects just X's. And pop takes a machine that expects only the stack X's and produces a machine that expects an X on top of the stack X's.
Right, I think I see. So the continuation of machine expects a stack of a certain type, and then the instruction will adapt that stack to fit. I guess that compiling a combinator to a machine means taking a machine that accepts the result and makes progress towards some final goal. So it's something like this then. Compile sub will take a parser returning an A, and then a machine that accepts that A along with some X's, and then we can build a machine that requires just that X's in order to continue. And the final continuation is going to be halt. It takes the one element on the stack and gives it back.
Right. So how would you translate combinators? So for example, the pure, which has type A to parser A, and app, which has type parser A to B to parser A to parser B.
Oh, easy. Something like this. So for pure, that's just the push instruction, right? With some M that will continue on afterwards. And then for app, we just need to compile PF, and then we'll compile PX. And after that, we combine the two results that are on the stack with function application using lift2.
Ah, neat. So, but what about the and then variant of app, where you discard the first argument rather than applying a function, something like parser A to parser B to parser B?
Oh, sure. All you need to do is pop after passing the first result. So you compile P, then you pop that result off, and then you compile Q, and then carry on with M.
Oh, neat. So I can see how this might work out. You know, now that we can see this is using CPS, it kind of reminds me of some work that my PhD student, Matt Pickering, has been doing lately on staging. Actually, there's a paper being presented at the Haskell Symposium about it coming up in just a couple of days.
Sorry, what's staging exactly?
All right, well, so staging is a form of metaprogramming where you can perform work on statically known results ahead of time, leaving only dynamic information at runtime. It's basically giving you fine-grained control over evaluation in your compiler. In our case, the shape of the machine for a parser and its combinators is static. In other words, it's known by the compiler.
I think I understand. So this means we can perform that translation from combinators to machine and evaluate most of it at compile time. I've heard of template Haskell, but that's untyped, right? It seems a bit of a waste of all the hard work we did to make everything typed.
Right, indeed. And I guess you haven't heard of type template Haskell. Unlike template Haskell, where you build ASTs, with typed template Haskell, you can only work with well-typed terms, which ensures that the process is safe. For example, if you have some term E of type A, then it can be quoted to get the code that represents E at runtime, quote E, which is of type code A. If you want to splice or run some code, you simply use the anti-quote by adding a dollar to the front. So for some code C of type code A, splice C gives back a value of type A.
Oh, so all I have to do is add code to the parts that are going to happen at runtime?
Yep.
Okay, so let's have a look at the machine state then when it's interpreted and see what we can uncover. So quickly, let's look at how we actually evaluate the machine normally with the run machine function. So we're going to provide some machine state gamma to the eval function, and that's going to interpret the meaning of each instruction in M. So all gamma is just our heterogeneous operand stack along with a return continuation for recursion, a stack for failure handlers, and the input X's itself. And so the bit that we can actually stage about this would be the eval function, because it's the machine that's known at compile time, right? So if I just add code around it, then that makes the function from machine state to final value part of code, and that will be done at runtime. And you can break this into a compile time function that takes code and returns code. That's fairly straightforward. But we should be able to do more than this, right? So the machine state gamma is always the same shape. So we should be able to get rid of that at compile time too. So if I push the code into the gamma, then we can ensure it only exists at compile time. Yeah, so at runtime, we'll produce a function with 4 arguments, 1 for each component, but the actual record's gone. But surely there's got to be more we can do now.
Well, the fact that HList in ops has the type X's implies that it must have the shape that we can know at compile time. And that's determined by the instructions also known at compile time. So you could push the code inside the HList.
I see. So if I map the code over the values in the HList, then the HList itself is only going to exist at compile time, and the values exist at runtime. And I guess that the structure of the handler stack is the same. It's determined by the instructions as well. So I guess we can operate with that list at compile time too. So with all things considered, I guess the only thing we don't really know at compile time is what the input is, and specifically what each continuation is at any given point. Everything else is gone.
Exactly, and that's why we like staging so much.
Awesome. So here's what the stage evaluation for push and halt might look like then. So halt will take the operand stack out of gamma and extract that top element and splice it into some code that builds a just for that value at runtime. And eval push, there aren't actually any quotes in the body at all, so it must purely happen at compile time. That's really cool. So I guess let's push our original example through this mechanism and see what code it generates. Wow, this is quite cool. So I guess we can see that none of the abstractions from the combinators of the machine are here at all. It's literally just a couple of functions taking as argument this good continuation and the bad continuation, and some input, and it'll all thread it round together. This is awesome.
Yeah, it is. It's really good. But there is a small problem. Most parser combinators, such as Parsec, have this combinator called bind, which is usually used to implement context-sensitive parsing. The stuff that was previously parsed can influence the grammar that is used to parse the rest. The trouble is that I don't think this can be staged.
That's a pain. I mean, do you really need to create a whole new parser that we can't inspect? What sort of things do you actually use it for?
Well, I suppose most of the time the grammar is static and bind is used to select the part of the grammar that's already known.
Oh, well, we've already seen an operation like that, right? It was case. So both of the outcomes are known statically, but you don't know which branch is taken until runtime.
Interesting. I wonder if this corresponds to Markov's work on selective functors. It seems to behave similarly to his branch operation, which arbitrates between two branches depending on a coproduct.
Yeah, I think that sounds about right.
Great. So if we give up bind and work with selectives instead, we can use staging, and that makes things really fast.
Let me quickly whip something up and we can see how it performs on some benchmarks I made earlier.
Wow, kids these days are really fast at programming things.
Perfect. It worked first time. That's unusual. Must be those strong types. Right, here's the results. So this graph is showing us that actually compared to the other combinator libraries, we're about 3 or 4 times faster, and we're even beating Happy. That's a parser generator library.
Wow, that's really good performance.
Yeah, this is great. Maybe we should write a paper about this.
Well, you're pretty good at coding things quickly, and I'm pretty good at writing papers quickly, so here you go. Cool. I'm going to stop recording now, I think.
Okay, thank you, Jamie and Nick. So if you want to join the authors for a Q&A in the New York time zone, then you can click on the link in the Slido room.